Welcome to our second talk for the afternoon. The topic is Ask the Graph. How knowledge graphs helps generative AI models answer questions. And we have the presenter, Michael Harvey, who is a senior solutions architect at Amazon Web Services. Mike Harvey is a senior solution architect at AWS with over 25 years of experience building enterprise applications. Mike is the author of 2 books and numerous articles. So Mike, you have our attention.
Great. Well, it's great to meet you all. My name's Mike Harvey. I specialize in knowledge graph, and I'm going to talk today about how knowledge graph can be combined with generative AI to answer questions. So I'm in a customer-facing role. I'm a solutions architect, so I have customer conversations all the time. And I've seen a surge in interest over maybe the past half year in combining knowledge graph and generative AI. So what customers are really asking for is to build something like a chat application that would allow an end user to ask a question in natural language and then to answer it with the help of an LLM. So they want to build something that looks essentially like this. And they've heard that about this thing called RAG, Retrieval Augmented Generation, and that it can improve this sort of solution. So the idea is that when the user asks a question, we tap into our own company database, and we get information from that database that's related to the question. And we basically provide that to the LLM as context. We, in a sense, augment the context that the LLM will use to answer the question. And the LLM will then answer the question with a nice natural language response. And the reason you'd use RAG is that the context you're giving is current, it's accurate, it's authoritative, and so the LLM will have the right context to answer the question with. It reduces the chance of hallucination. Now, the notion of graph RAG has come along, which is essentially the same as the main RAG pattern, except the database is a knowledge graph. In the previous figure, the graph was just any old graph, any old database that you have, but here it's a knowledge graph, and this is supposed to be better. And the reason it's supposed to be better is that a knowledge graph has really knowledge. It contains knowledge. That's what you're tapping into. And really, what is knowledge? That's a pretty bold claim, but a knowledge graph has connected data, really a connected set of facts, a big web of connected facts. So if we're able to tap into that and give it to the LLM to answer the question with, that's probably better. The idea is right, I think, but I think you'd have to prove this out and actually build it and see if that's the case, but it certainly has promise, this approach. And because all the data in a graph is connected, what you're bringing back is not just the immediately relevant facts that tie back to the user's question, but also facts that are related to those facts. And then you can go several hops deep. You can bring in many hops in the graph. So that's pretty good. There's also a degree of explainability to this result because sheer connectedness really gives some explainability. If I'm giving back not just facts, but the facts that are related to those facts and so on, that just seems stronger. It seems to have more explainability. So this is the approach that I'm going to talk about today. I'm going to kind of talk about how you would build this. And I do show in the diagram, you can see at the top right corner, we have the 2 main camps in the graph world, RDF, the Resource Description Framework, and then Apache Tinkerpop. Both are very popular. I'm a big RDF fan, but I think I'm in the minority. Tinkerpop really dominates this space today. So I'm going to look at 3 ways in which I've seen graph RAG being built today. This is a moment in time. Things are changing every day. But I've seen 3 patterns in particular kind of have been attempted to this point. The first one I'll call NLQ, Natural Language Question. And it's really the idea that when the user asks a question, a natural language question, what we'll try to do is have an LLM generate a graph query that corresponds to the question. So what you would need to build this is, first of all, you will have a knowledge graph with some data in it. In this case, it's a graph consisting of airports and the routes that connect them. So that's my data. And the LLM is going to generate the query. It needs to know what this data looks like. So what I need to do is introspect my graph database, pull a schema from the database, and provide that as context to the LLM. And in this example, we're using the LangChain Neptune QA chain for OpenCipher, which exists today. And I'll show a link later if you want to try this out. So the user can ask a question. So let's say the user wants to know to find routes from YOW to MHT. YOW is the Ottawa airport, MHT is Manchester, New Hampshire. So how would we do this? Essentially, the LLM, knowing what the schema looks like in the database and knowing also how to write OpenCipher, can create a query. And you can see highlighted kind of in the middle of the figure is a match clause. So this is an OpenCipher query that is actually correct. What it will do is find the routes to connect YOW and MHT airports. It will actually go several hops dynamically to do this. And then the LLM, provided, once it has the result, and bear in mind, the LLM generates a query. We're going to actually run that against the database and see what we get back. The LLM can generate a nice response. So you can see here it's giving a description of the routes that connect Ottawa and Manchester. So this approach has some merits. It allows you to bring your own knowledge graph. So you don't have to tailor your graph to fit the approach. It will work with whatever you have in the database. So that's good, and it's great for structured data. It does require that the LLM can write queries in a language like OpenCipher, Sparkle, or Gremlin. When we tested it against GPT-4 and Anthropic Claude. Those did pretty well. But even so, the LLM can write a bad query. And so there are some ways you can mitigate the risks. You can do kind of a few-shot approach where besides having the LLM use the schema, you can give it some examples, and that might improve things. It helps if your graph schema is simple. If it's really complex, the LLM will have a hard time. So try to keep it simple. If your schema is very large, maybe use a subset of it. And a more advanced approach might be if the query is bad, try to parse and analyze the query, and maybe then ask the LLM to fix it and try again. So that's a fairly advanced approach, and I have a link here to a research paper on how to do that. And it may be that the query is fine, it's just inefficient, it's too slow, it times out. And in this case, you may want to have your database architect look at the query, do some analysis, and maybe do some prompt engineering. Ensure that the LLM won't write you a query like that again. Another kind of a related approach would be to have the LLM, instead of having it write queries, if you can put an API in front of your database, it's kind of a facade layer in front of your graph database, just have the LLM call that, figure out how to call that. You'd have to tell it what the API looks like, but that may be simpler and more successful. That's kind of the agent approach. So the second pattern I'm going to call KG-Gen, or knowledge graph generation. It's quite different. It's more about unstructured data. And so we would start with some unstructured text. In the upper portion, you can see we have an excerpt from a press release about Amazon opening a fulfillment center in Mississippi. So that's just loose text. What we would need to do is to create a graph from this. So we want to convert text to graph, essentially. And so you can see in kind of the center of the screen, we have a graph model where the circles are entities like Amazon, Mississippi, fulfillment center, and we have edges connecting them. So Amazon opened a fulfillment center. The fulfillment center is located in Mississippi. So we have a graph as a result of all of this. And an example of a framework that can do this would be the Llama Index Neptune Knowledge Graph Store. And there's a link to that in the bottom here. And later I'll be providing a link if you want to try this out on your own. In order to make this work, I need an LLM that can do entity extraction. So that's a crucial ingredient. That's how I get the text and find the entities and facts in that text. So the query, suppose the user wants to know, does Amazon have a fulfillment center in Mississippi? The way in which we would do this, since we have the graph data arranged in a way that's pretty generic, we just run a generic query. It's a templated query. It doesn't need to be generated. It's completely generic. And so it's an open cipher match again, just looking for any facts that we know about any of the entities mentioned in the question. So Amazon is mentioned in the question, so is Mississippi, so is Fulfillment Center. So we can just run a generic query to find out about all of those entities, everything that we know about that. We can go several levels deep. We can facts related to facts related to facts. All that's provided to the LLM to answer the question with. And you can see in the bottom left, it comes, the LLM can actually summarize it, all of this context into a really nice answer. So some considerations about knowledge graph gen. It's not a bring your own knowledge graph approach. The framework wants to determine what the graph model should look like. And it can get away with that because it's an opinionated model. It claims to have a good way of solving this problem, but it does want to control the graph model in order to do this. The approach has the benefit of having a generic query. I don't have to worry about generating queries, which can be very error prone. So I'm using a completely generic query. And generally, this approach is great for unstructured data. It doesn't work so well for structured data. It's not really meant for that. And also, kind of a major problem with the approach, an unanswered question, is if I do have data already in my graph, how would I link what this framework produces to that data? That's actually a hard problem to solve. The last approach, the last pattern really is connected chunks. And it starts with unstructured text again. So in the upper portion of the figure, you can see the same paragraph about Amazon opening a fulfillment center. We want to be able to generate graph from this. What's different about it is we're not going to extract entities this time. We're just going to chunk the text into small pieces and create vector embeddings for that chunk. And the vector embeddings will be there basically so that we can search it, do a similarity search on chunks. And so what we end up with in kind of the middle left of the figure is a graph model where there's really two colors of nodes. There's red and blue. The red is the chunks and also the documents that they belong to. And then the blue is kind of structured data that I already have in the graph. So I may already have organizations, people, places. I may already have that structured data. And I want to be able to link the red to the blue. And so in order to do the embeddings, of course, I'll need an embedding model. When I tested this out, I used Amazon Bedrock to use an LLM through Bedrock to do the embeddings. And the query, let's run the same query we did for the last pattern. Does Amazon have a fulfillment center in Mississippi? The query is generic. It's templated again. I do a top K search this time. Basically, find me chunks that are similar to the question being asked. And for those chunks, do some more traversal in the graph to find related resources and facts. Those will be the blue nodes. So the way this would work is I find the red chunks, and then I find the blue nodes that are related to those chunks. And that's the context that will be used to answer the question. The LLM will use that. And you can see in the lower left a nice response again. The LLM does a really nice job taking that context and responding. So some considerations here. This is about unstructured data, and the model had red and blue nodes. And I chose those colors kind of for explanatory purposes. If you only had red, you wouldn't need a graph database. If you only had red, you'd be doing baseline RAG, essentially. You could use OpenSearch or any number of solutions for that. So it's really by combining the red and the blue that you have graph RAG. And this approach does have the benefit of being bring your own knowledge graph. So the blue nodes were structured data that I already had, and I'm able to work with that. I'm able to bring in this unstructured data and actually link it to that. So that's good. This approach also uses generic query. That's a good thing. Kind of the issue, though, is that how would I link the red to the blue? All we have is text. Maybe we have some tags or keywords to help us, but otherwise we need to do some sort of entity extraction in order to connect the red to the blue. So I want to kind of bring together some of the ideas to solve a problem, and let's take a case study, deal research in investment banking. And so the use case is we want to be able to allow investment bankers to ask questions to research different deals, mergers, acquisitions, that sort of thing. They want to be able to use a chatbot. Questions they might ask include summarize deals where the buyer is a FANG, or summarize deals in bid history where company X issued a counteroffer. So these are natural language questions. The users don't know anything about how to write graph queries, but they certainly want to know the answers to questions like these. It's not easy given current, this investment bank probably has never been able to support such an interface before. So it's not easy to meet this requirement. Let's add an additional requirement that when we answer the question, we also want to show where the answer came from. So we want to be able to, if the answer came from an SEC document, for example, let's show which document that is, where it came from within that document. So what we would seek to build then is a graph RAG style solution that needs to really combine the chunk and extracted approaches. This just gives us the most possible ways to search the graph. And really what we want is to model the graph so that it would support an extremely dynamic searchable interface for a graph. Until now, graphs have generally not been extremely dynamically searchable. So we'd like to build something like this, and even if we decided not to do a chatbot, this would still be an enormous win to build something like this. So, but having said that, let's assume that we do want to build a chatbot. This extremely dynamic search capability would be providing the context for the LLM to answer these questions. So a couple of, I want to kind of go through the data model for this first. And so we have really three colors of nodes or resources. We have red, blue, and yellow. So the reds, as before, are the documents or chunks. This works exactly like I described previously, that we have vector embeddings in the chunks. And we attach some provenance to the documents. Provenance meaning like who wrote the document, when did they write it, where can we find the document, what is its change history. This is really important because we need to actually provide this. It's a requirement to provide this provenance when we answer the question. And graphs are good at provenance. Graphs have ways of doing provenance. So we'll definitely tap into that feature of graphs. The yellow nodes are the extracted entities. The blue nodes are the structured data. The structured data, in this case, is what you would expect if you're researching deals. So we have companies, we have deals, we have deal roles. So a company will play a role in a deal. It might be a buyer or seller. It might be the legal team. It might be the financial advisor. So we're kind of fixing the problem I mentioned earlier about linking the red to the blue. And we're doing that through entity extraction. So you'll notice the yellow in the yellow, we have a fact expressed as a graph. So John Doe is a lawyer representing Lincoln lawyers. We got that from the document. It mentioned that. But what we'd like to do is tie that to the blue. So John Doe is some sort of person. Lincoln Lawyers is some sort of company. We'd like to link those to existing persons and companies we already know about in the graph. So one way in which we can do that, and this taps into a capability of graph, is to use really a rich naming scheme. So when we have an entity like a company or a person, give it lots of names. We'll have our own business name and ID, but also give it alternate names and show other IDs or URIs that are used to refer to these entities. DBpedia is a well-known kind of graph on the web of just general knowledge. So it has URIs to refer to things like people and organizations. Let's use those because this gives us the best chance to actually find things. If we can find them by any number of names. So, and it would actually allow us to do some entity resolution. So you can see it in the left, the document mentions John Doe. We also have a John Doe in our graph in the blue. So how would we match yellow to blue? When we do entity extraction, ask the LLM to give us not just what it found, but alternate names and well-known IDs for what it found. And that's one way in which we could do the entity resolution. By no means is entity resolution that simple, but that gives us a strategy to at least get started with entity resolution. Also taxonomy. So in the lower right, we have a taxonomy of industries. So you can see that we have legal industries, and under that we have corporate litigation, intellectual property. We have banks, we have tech. Notice that there's alternate names for all of these. So big tech might also be sometimes called FANG or MANG. And this is useful because if they ask a question about FANG, we can kind of tie it to big tech. We can find companies that belong to big tech. We can tie things together nicely by having a taxonomy. And then finally, inference or reasoning. Graphs allow us to expand what we already know with inferences. And there's a notion of an ontology, which is kind of like a graph model that supports inference. So I could, for example, have an inference rule that says if a company should be given the property strictly legal role if all of its roles in deals to this point have always been just legal. And so that's it makes sense that that would logically follow. But once we know this, it allows us to more efficiently answer questions like, tell me about companies that are strictly legal. And so a quick and dirty design for this, we have a chat application. Let's build something like a graph search service, which the chat application would use to answer questions. The search service would get its data from a knowledge graph. In this case, I'm using Amazon Neptune as that knowledge graph. And it would also use LLMs through Bedrock to do the entity extraction, do the embeddings. And so if the user asks a question like, summarize deals where buyer is Amazon or another FANG company, the way in which I would break this down is, first of all, I'd find information about Amazon and anything we know about Amazon, really. And that's really in the yellow and blue part of the graph. I would do the same thing with FANG. But what's interesting about FANG is that it's really an industry that a company might belong to. But because it's a graph, I can tie all this together. And then I'll also look at the chunks, because the chunks may have something related to my question. If I find that, I'll then bring in the related yellow and blue nodes that are tied to that chunk. So I'm going to wrap up now. By way of summary, customers are really interested in the combination of knowledge graph and Gen AI. I get several calls a week on this, so everyone wants to know about this and its potential. And we looked at 3 graph rag patterns, NLQ, KGGen, and connected chunks. So people are fumbling their way around trying to figure out how to solve this, and those are some early attempts. I'm sure things are going to change over time, but So far, these have kind of stood out. So the recommendation that I had in addressing the deals case study was to use a kind of a combination of these approaches, to use chunks and extracted entities, but also to bring in taxonomy and ontology, and to ensure that we can bring in our own knowledge graph, that we don't have to have the framework tell us the graph. We can use what we already have. So as a call to action, if you're interested, I'm showing 2 links here. The first is a Git repo, which has really the 3 patterns, if you want to look at code examples of those 3 patterns. It doesn't have the final solution. I'm still building that out, but you can see kind of how the 3 patterns work. And then we do surveys. AWS, everything is data-driven. So a quick survey on the second link. If you're interested, it takes a minute. And give your feedback. We'll give this talk in the future. We'll incorporate your feedback for sure. The last slide I have is just kind of like a final question slide, but I want to keep these links up, so I'll just freeze it here. And that's all I wanted to present, but I'll now take questions.
Hello. Hello, good afternoon. So earlier you showed like a framework where you use an LLM to extract the entities coming from like free text, right? I'm just like wondering, how do you ensure that the LLM is able to extract proper entities and not, like creating like new entities that you don't expect? And also like, how do we make sure that those entities, like say names and organizations, are perfectly extracted so that we could build the graph properly?
Right, and at this point, it's not perfect. It won't do a perfect job. And prompt engineering will help. You can give it lots of advice on how to extract entities, including things like give me alternate names, give me well-known URIs, maybe further advice beyond that. But what you will find is that it's highly imperfect, and that things like entity resolution will definitely be part of this initiative. And also that you're going to have to look at what it produced and maybe eyeball it and see how well it did, and probably fix it up a little bit.
I see. And also, like, does that also apply to the type of relationship amongst these entities, right? Like, because like extracting the entities is one problem, and then another problem would be like how to connect these entities together. And earlier, like there was an example where like a person is connected to a company, etc., right? And those are all opinionated coming from the LLMs, right? So it's also a different problem altogether. Is it also part of your like roadmap, or like any suggestions on how we could probably remedy that if we do our own implementations?
Yeah, all of those things you mentioned are problems that you'd need to deal with. I guess roadmap is kind of testing this out and continually perfecting it. I think that's what everyone will face right now.
I was wondering to know that if there is an element of time that can be applied on the graph, because let's say, like we might find a chunk of data that is seems to be more relevant, but there are like less relevant but more recent parts of the data that are actually more relevant to the user. If I can.
Time? Did you
Yes.
say time? Yeah, I suppose you're right, because especially with unstructured data, the more recent it is, maybe the more relevant it is. An old article may be less useful. So certainly in a graph, you have the ability to represent, as part of the provenance really, when the artifact was produced, when the document was produced. You could actually filter on that. When you're searching for relevant content, you could do a time filter for sure. The provenance is there. And you can certainly, this would not just be for time, but also who wrote it, who wrote the document. Maybe there's more authoritative authors than others, so you could also filter on that.
have you tried extracting events? So like not relationships, but rather, let's say somebody is getting married and you have a spouse edge between two entities, or let's say acquisition would be a better example. And then how do you represent that as a graph?
Events versus relationships, really?
Yes.
It's really the same way. It's, imagine two nodes connected by an edge. That's a fact. That fact could be an event. Since we're talking about mergers and acquisitions, that could be like an offer to buy or something like that. I think it's really the same approach, but there are actually tools that are really good at just looking for events. Amazon Comprehend is an example of this. So if you're interested in just events, you could either tailor the LLM to look for those, or you could use a specialized tool that can just look for events. All right, anything further? Awesome. Thanks, everyone.